Yes. 6.47 power minus 3 divided by 1800 divided by 20.833 power minus 3 is 172. So I bring this down here, right? I get this number. Yes. Omega naught squared. Wait, say it again. 0.0, where do you get that from? This one? Oh. Thank you. Yeah, I was hungry. Where are you? One orange juice. Yes, please. Beer is cheaper than me than orange juice, okay? I don't buy cheap orange juice, okay? I buy the good stuff. Okay, thank you so much. The one looks weird. So the answer is 19.034. I was hungry, I think. Okay. Okay. That is the end for mechanical vibration. The next time you're going to see mechanical vibration is in your third or fourth year, depending on what stream that you go to. But at least now, all of you have an impression of mechanical vibration. And when you do your math, what are you all learning in 2ZZ03 now? Second order differential equation already? Not yet. But when you come to second order differential equation, when they talk about mechanical vibration, you say, I understand what it means. Okay, let them solve up the math. There's another video I want to show you all. Yeah. Move on. Okay. What you see over here are three structures. Okay, as you can see. And I want you to apply what you have learned. Okay. So what's happening is you have three structures, one on the left, the center one, and on the third one on the right. Assuming that the mass is constant, the table below will move left and right. Okay, the table below will move left and right. Can someone tell me which one will vibrate first if we increase the frequency from 0 onwards? The right one will vibrate first, or the left one, or the center one? Anyone? Which one? The right one. Why? It looks less stiff. Right? Oh, good. What formula will you apply? Don't look at me, look at your notes. What formula are you going to relay? Week number 1. Any idea? Worrying now. So we mentioned that stiffness K is equal to what? AE over what? L. Did we do this or no? Right? Did we write this out? Somewhere we wrote this out, yes or no? is here, and then we went here, and then he kept on blabbing, and I don't know what he's blabbing about, right? And then we reach here, right? Can you all see here? AE over what? L, yes? Now, this is only possible when it's what? When we derive this, is the structure is under axial loading, right? So we have a structure over here. Oh, let me draw it initially. And over here, we pull a force, and this is our P, okay? So our P over here is a constant. Now our P can also be equal to P Y sine omega naught T, okay? Now, come back to here. Cross-sectional area of the beam all the same. Young's modulus all the same. The length is what? Different. The longer the length, the lower the what? Stiffness. Okay, let's on with some music. We are all going left and right, left and right. With time proceeding further, what will happen? Now you see some vibration over there. It's because the structure from left to right are not isolated. If you do them individually, okay, you won't see that vibration at all. I want you to see how the structure is loaded. So Eugene, the center is going, not yet, not yet. Okay. And you see the one on the right, it's going, gone, okay? Okay, it's gone already. It's resonant, okay? 4 hertz. I want to go to Canada Wonderland and does that, you know. Okay. So when they increase, now you look at this, you understand, right? When they increase the frequency, right? So now they are progressively increase the frequency, right? It dies off. Now you know why. So the next one is which one? The center one, yes or no? Because the center one is the second or the second steeper one, right? There it goes again, right? And then you have the it's gone or it's what? Resonant. Okay. And then when they keep on increasing the frequency, so now you can see, I want you to focus on the stage. The stage is going what? Left and right. Okay. Okay, now you see that. Okay, now what I want you to do now since you see how the structure behave, I want you to do this now, right? Okay, now what I want you to do is I want you to sketch, okay, how this structure will look like when you carry out your analysis. Is it the same, right? Is it the same as axial loading? I repeat again, is it the same as axial loading? You have to relate what you see in real life back into like paper again. You cannot just like, I take the picture and I just paste it. There's no analysis. So how are you going to analyze this structure? On the mass, is it free to move? Yes or no? It is free to move, right? So if I'm going to sketch this, is it going to be the same as under axial loading? It will not be the same anymore, is it? Okay. So if I'm going to sketch this, it will look different now. Okay. So how different it will look like? Now you realize that the deflection is left and right. Am I right? Not up and this is what? Up and down. Now it's what? Left and right. Okay. So it's not the same. So I'll sketch down here. So again, this is our beam. Okay. And then on top over here, we have our mass. Can the beam move up and down? No. So what boundary condition should be at point A? Anyone? What condition has to be at point A? Okay, so the condition we have at point A is going to be what? On a roller, right? Roller means what? If I have my transformation, this is X and this is Y. When I have my transformation over here, roller means what? Y is equal to what? 0. Am I right? Okay. And what will happen next is now the structure can move what? Left and right. So for this case, X is not equal to what? 0. Now the excitation is equal to Px is equal to, or P, the excitation now. I'm going to draw on this side now. P is equal to Px sine omega naught t. Yes. Say it again. P is the force that's applied at point A, at A location. Oh, let me, right? So if we were to come back to here, if we look at this structure now, what is stiffness equal to? Now, the structure, when it deflects, is it deflecting up and down now? No, it is deflecting in this direction. Okay, so I'm going to draw the deformation pattern. So the deformation pattern will do left or will go what? Right. Okay, so this is the deformation pattern. Okay. Now, the stiffness now changes. Now K is equal to EI